Alright, welcome to lesson 1.04. This is going to be a pretty great lesson because we're going to take a look at some sets of data and actually fit some functions to model those data sets. And this is a really handy skill in general in real life. Before we get to that, I want to put up a couple of problems for you to work on that relate to some of the previous work we've done with quadratics, and this would be a good review and good practice in working with quadratic functions. It's not mandatory, but I highly recommend that you do it. Alright, so what I want you to do to get this started off is to take a look at linear and quadratic functions. What I want you to do is sketch what a linear function looks like, sketch what a quadratic function looks like, and then try and figure out what some of the key differences are. So go ahead and give that a try on your own. Okay, so here are the sketches of the general form of a linear and a quadratic function, and then of course the general form for both of those functions. And the key difference is actually in the function itself, in the algebraic representation, and you should be able to pick up on it if you look carefully. And the key difference is the way in which the y values change depending on the x values. So notice here that for a linear function, every time you change x by 1, you're going to increase your y value by m, right? That's called the slope. However, if we look at a quadratic function, notice that if I were to, for example, change the x value from 1 to 2, so if I did 1 squared, I'd get 1. But if I were to plug in 2 for x, 2 squared would be 4. So instead of just increasing by one a value, I would be increasing by 3 a values, right? First I had 1 times a, and then I would have 4 times a. And then go even one step further, okay? Think about going from 2 to 3. Well, 3 squared is 9. And so 9 is actually 5 bigger than 4, and so then I would have 5 more a's. And so notice that each step of the way, your y value is getting bigger by more and more. In other words, the difference between the y values for a quadratic is going to change, whereas for a linear, the difference between the y values is always going to be the same. It's always going to be the slope m. And so that's the key difference. So go ahead and copy that down in your own words, and then we'll go on and we'll take a look at how this will help us make sense of some data. So here I've captured it in kind of my own words, and I want you to take some time and be ready to talk about this in class, about how these different ways in which the y value changes are evidenced in the way that the graphs look, okay? And you might want to consider the steepness of different parts of each graph. Okay, so with that in mind, with these key differences, let's take a look at how that might show up in some data. Okay, so let's see if we can determine now, based off this characteristic, whether a table of values would be best modeled by a linear or a quadratic function. So for each of these data sets, your goal is to determine whether or not the function that takes these x values and outputs these y values is linear or quadratic. Which one would be best? So why don't you go through and try the first one on your own, and then we'll talk about it. Alright, so if you're looking at this first one here, and you think about, okay, well, the x values are increasing by 1 each time, so let me see if I can look at the difference in the y values and see whether or not they're going to be the same or changing. So I subtract 8.9 minus 6.8, I get 2.1. 11 minus 8.9, I get 2.1. And if I do 13.1 minus 11, I'll get 2.1 as well. And since the change in x is always going to be 1, then I'm finding out that this is going to be most definitely a linear model. Okay, why don't you try B? All right, so here if we take a look and subtract and find the differences, we'll see that while the x value is continuing to change by 1, the y values are changing by a lot more each step of the way. And this should be a clue that we're not dealing with a linear function, right? If you think of a nice straight line, every time you make one step in the x direction, you're going to go up by the same amount or down by the same amount in the y direction. So we can say that this is a quadratic function. But I want you to look a little more closely and see if you can pick out a trend that's not just happening between the y values, but between their differences. So take a look. What's the difference between 39.75 and 125.25? And what's the difference between 125.25 and 210.75? And if you look closely, you'll see that the difference between the differences, so let me say that again, the difference between the differences are going to be equal. And as we move on in our math career, we'll learn more and intuitively understand more why that is. But this is a very cool pattern that we notice for quadratic functions. And so this is going to be something that we're going to want to add to our list of key characteristics for quadratic functions. All right, so I want you to try C on your own. Use some of the concepts that we've just discussed to your advantage. We'll discuss this in class, and then when you're done, press play again, and we'll capture this key idea in our notes. All right, so here is the kind of the key point we've honed in on. So for a linear function, the difference between the y values is constant. Whereas for a quadratic, the difference between the y values is not constant, right? But the difference between the differences is. And to help you kind of understand this, you can go back to the graph that the sketches that we mapped out, where if you have a linear function, every time you move the same distance in the x direction, you're going to step up by the same amount in the y direction. However, for a quadratic, notice that as you make steps in the x direction and look at how much you're moving up in the y direction, those values are going to be not constant. In other words, if you look, even though I stepped the same amount each time, the change in the y was very different. However, the difference in the differences, so the difference in the differences, so that would be this amount right here, is always going to be the same. And that is a key characteristic that we can keep with us. And so as we build our repertoire of functions, we look at exponentials and radicals and so on and so forth, we can continue to differentiate from the functions that we already know. All right, so I hope that was fun and informative, and be ready to look at some more data in class tomorrow.